Guys, today we'll be solving LeetCode number 153, find minimum in rotated sorted array. It is a medium difficulty question on LeetCode, but it is also the daily problem for today. Now, the question statement itself is a bit misleading in the sense that, they are correct in the fact that if you are given a sorted array, right? And if you've done circular arrays or like shifting, essentially as they say, is when you have an array, right, and you want to shift it by one, it just means essentially just going like this in the array. So whatever was on the last index will now be on the first index, whatever was on the first would be on the second, so on and so on, right? That's what it means to be rotated. And in this question, what they want us, what they're trying to explain is the rotations and stuff. But if you've detected a common pattern, then it's just essentially just finding the minimum in an array. That's literally all they want. And this obviously you can do it in O of n time. All you have to do is just keep a minimum counter and just figure it out and then do it and then just return it. This takes O of n again. I want to explain this because it is pretty simple in implementation, and that's not what I'm here to explain. The approach that I want to explain actually is the O log n approach. And what's this? Well, binary search. Obviously, because we have to find an element, and the best way to do that, binary search. I've done a previous question, so find peak element. Yes, if I'm not wrong, find peak element is a very similar question. So if you can solve this, maybe try that out. If you've come from that, then the approach on this is a little bit different compared to what I did over there in this question. So the thing is, if you envision the array first, okay, if we draw out a line on how these would look like on a graph, 3, 4, 5, it's ascending, right? And then we have a decline, let's just say, right? Because we went from 5 to 1. So if we think about it, it's like the array will always, because the one that's given is sorted, right? And like I said, the one at the end becomes the first and things like that. You would either have like a constant sorted array, right? Or you would have something like this, where it would be sorted up to a point and then it would be decreasing. It would decrease at some point and then it would be sorting again. So if you take a look at example 1, that's a very good example actually, 3, 4, 5, 1, 2, right? I've written it out here. It's sorted up to a point, then it falls, and this part, it is technically sorted, but in comparison to the peak between these two, 5 and 2, we have dropped, right? Now, how do we determine which side to search the minimum on, right? We're not given the array as sorted, we just know that it was sorted and it was shifted some places. So how do we do that? If you look at the 3 examples, 3, 4, 5, 1, 2, 4, 5, 6, 7, 0, 1, 2. Let's consider the very basics of binary search. So let's consider our middle point, okay? So that would be 5 in this case, 7 in this case, actually 1, 2, 3, 4, 5, 6. Let's write this out actually really quickly. 6 plus 0 divided by 3, yeah, correct, 7. And in this one it would be 13. Okay, how do we know whether the element that we are sitting at, right? What we have to discern is the fact that are we sitting at a part which is rotated is sorted ahead of us? Is it sorted ahead of us is what we want to see. So like I said, if we are sitting at 5, right, and we see the very 1 and 2, we see that though it is sorted, but it is less than us, right? And in the array itself, there's only one point at which like it falls, right? And we want to do minimum, so we would want to approach the side that it falls, right? So if we see that, okay, we check it with 2, we check it with the very end of the array, because if it was shifted 0 places, then it would mean that it is a regular sorted array and the maximum is sitting at the -1, like the very last index, right? So if it is shifted 0 places, like this example over here, then 17 is the maximum that we can find, right? So how do we discern whether we are in the sorting part of where to like go actually? And then obviously we just check it with the right. So in this case 3 4 5 1 2, we checked it with the right, right? We saw 5 and 2. That means up until 5 we are sorted, right? 3 4 5, that means 3 4 5 is sorted, but there is a fall, there is some sort of a fall, right? We don't know what value is the one that's after 5, but we know that there's some sort of fall that causes the value on the right to be much lower than what we are at. So that's what we have to decipher. And how do we figure out the minimum in between this like sorted but smaller than us array? We do a binary search on that particular part. So in this case we would take out 1 and 2, right? We will look at this, we would take out 1 and 2. All we are doing is mid plus 1, by the way, but that's it. We just look at our right and we see if we are greater than the one that we have at our right, worst case scenario, it is the maximum. If we are greater than the one we have at the right, that means after me we fell somewhere in the middle and I have to find my minimum element along those lines. If not, and if I am the one who's sitting, so I'll take example 3 now. 7 has a very close example, so if we envision 7, right, we check it with 2 as well, and we see, okay, this part is sorted, right, but it has a decline, right? That means we have to find the minimum somewhere along our right side. Now let's consider the example 3. Okay, example 1, 2 and 3. 11, 13, 15 and 7, we were at the middle, we checked with our right. Okay, we see that our right is greater than us. That means we have a sorted portion, right? A sorted portion. And keep in mind, if you're thinking about duplicates, the question states that it is unique, so that issue is completely, you don't have to worry about that. Now 11, 13, 15 and 17, we see that 17 is greater than us, right? That means we're in a sorted portion of the array. If we are in a sorted position of the array, do you think that going to the right would make us get a more minimum element? Obviously no, right? The ones to the right will be greater than us. So we would section it off and we would say, just consider between me and the ones that are smaller than me. So we will look at 11 and 13, right? And we can't discern whether it is a minimum element because we can't do a mid minus 1, mid plus 1. There is no way to do that, right? You can't check every element when you have that. Like you can't go to the middle and then go across the entire array and say, okay, I'm the middle element. That's like O of n complexity anyways. So okay, 11 and 13, we have that, right? And when we sit at 11 and 13, right, how do we know when we are at the minimum index? So 11, 13, let's take this example. Now we will have 0 and 1, right? We will do a recalculation, floor it by 2, we will sit at 0, and we will see, okay, 0 is now 11 is our mid, right? 11 is our mid, and we will check it with the right again. So we see that, okay, we are less than our right. So like I said, do you think we will find it on the right side? Obviously not, right? So we want to propagate it back into 11. And as you can see, both the pointers L and R actually point to it, right? But all we can do is at the end just return nums L. So now I'll write this out in code. If you've understood the logic of the question, this one isn't that easy to, this one isn't that hard to code up, sorry. Uh, like I said, if we are greater than the one we have at our very end, then don't consider myself, consider everyone else above me, and then r equals to mid otherwise. Include me when you try to find for the minimum. And at the end, just return your left pointer. And that's pretty much it for this question.